The last talk of this symposium will be given by Steve White. Steve's a professor at UC Irvine. He's well known as a pioneer in the numerical study of quantum systems. In particular, he created the density matrix renormalization group in 1992, which from a practical point of view essentially solves all quantum many-body problems in one dimension and is still going strong today, 20 plus years later, even beyond one dimension. It's the kind of the backbone of a revolution that's going on, which is bringing together quantum information theory and condensed matter physics. And Steve is in almost a unique position to tell us a bit about some of that. He's a fellow of the APS and a winner of the Raman Prize of the APS. And he'll be telling us about numerical studies of strongly correlated systems. Hopefully it hasn't changed. Beating the exponential growth in computation time. Thank you, Steve.
Thank you, Leon. It's a great pleasure to participate in this Kavli Symposium. And it's a great pleasure to tell you about at least one view of the status of numerical methods for the many electron problem. Of course, I'll have to have a narrower view than the whole subject, and so I'll first tell you about the part that I'm going to cover, which is sort of the near exact type of simulations, which include exact diagonalization, various forms of quantum Monte Carlo, and then DMRG and tensor network methods, which have come up in Steve's talk, certainly. And along the way, I'll talk about this issue of, is there a general solution to the sign problem? And it turns out that the answers that you get about the general solution apply not just to quantum Monte Carlo, but it apply to any other method that you might think of. And then talk about this sort of new idea that unifies DMRG with these other methods. That's the idea of low entanglement. And along the way, I'll give examples. I won't have time to go into a great deal of detail on these various examples, but they'll be focused on Hubbard, Heisenberg, and TJ models, and spin liquids, and cuprates as sort of the focus point. Okay, so numerical approaches are at one point, we sort of had to defend the use of numerical approaches in studying some of these systems, but those days are past. It's broadly recognized how important they are, and there's a huge number of numerical approaches. So they range from density functional theory, which has an important role not just for weakly correlated systems, but to frame the problem, to tell us what the important structural and orbital aspects of the problem are in strongly correlated systems. And then we have a whole set of methods that try to go beyond go to somewhat stronger correlation than DFT can readily handle, and still include all or most of the electrons. So this includes techniques like DMFT, density, dynamical mean field theory, and DFT, and diffusion Monte Carlo with fixed nodes. Then we have the class of materials that take something like the Hubbard model and take a look at that and don't worry about, directly worry about all the other electrons. And there are approximate treatments of those. So again, DMFT, various forms of variational Monte Carlo. And then the ones that I'll focus on, because that's been the area that I've worked in the most, are the exact or near exact methods. And so those are the ones where they're either exact, and we'll look at exact diagonalization. They may be exact up to statistical error, such as some forms of quantum Monte Carlo, or they may have a systematic control parameter that allows the error to be minimized arbitrarily given a big enough computer. And the key issue in all of this is that these exact or near exact methods tend to have an exponential growth in computer time, either with the size of the system or sometimes the inverse temperature or the accuracy. And progress in developing these sorts of techniques has come from finding a particular class of problems and finding a technique that works and beats the exponential for that class of problems. And so then you set aside and you say, we can now solve these problems. And I'm going to argue that there will never be a method that solves all of the problems, but we can continue to work to break off pieces of the problem and solve selected classes. Okay, so let me start with exact diagonalization. So let's think about diagonalizing a spin system, spin 1/2. So there's the Hilbert space is 2 to the n, where n is the number of sites. And the most naive approach you might do would be to form this 2 to the n by 2 to the n matrix, diagonalize it with the dense matrix eigenvalue routine, and that would cost you a computer time of 2 to the 3n. A much smarter way to do it is the Langshos algorithm, which only works with one vector and does it iteratively. And so this gives you both a calculation time and a storage time that's only the size of the Hilbert space, 2 to the n. And then you can reduce that further with use of symmetries, but it's still exponential. Despite this exponential, the exact diagonalization technique is still extremely useful. And so I wanted to bring up this particular impressive example of exact diagonalization that I found particularly useful. This is a treatment of the Heisenberg model on the Kagame lattice. And it goes up to a total of 48 spins with an exact diagonalization. So here's the Kagame lattice. It's known to be one of the very most frustrated spin systems. And it's been a candidate for a spin liquid for a long time. And recently, we've made a lot of progress in showing that it is a spin liquid. And I'll say some more later about the DMRG work on that. But let me focus now on the exact diagonalization. First of all, you can see the size that they're working with, even with all the symmetries. And this is, in terms of computational physics, this is a very impressive calculation with thousands of nodes and the number of states here in above 200 billion. And what does this tell us? And this is a two-dimensional system, so you might not think that exact diagonalization could tell you too much. So if we look at the results, one of the exact diagonalization always gives you results that you know are right. You only have to worry about the fact that it's a finite size. And it gives you a lot of detailed information. So here are all these excited states. And you see a few low-lying states, but what I want to focus here, there's even a gap spin liquid will have a few low-lying states, but here, let me focus on this broad region here where you see it looks like there's a bulk gap. And in fact, I'll claim that this is a bulk gap. And so if you, this is with 48 spins. If you step back to a little bit earlier results, back with 42, the size 42, this bulk gap was half the size of this. And back to 36 sites, it was half the size of that. And so it really looked like the system was gapless for a while, and that led the field a bit astray. But now, cranking up to this impressively big size, you see this bulk gap appearing, which is what we had found also with DMRG. And it's always nice to get two different methods that give you the same result to know that it's really right. Okay, so this is an example of just brute force dealing with the exponential growth. But how about getting rid of the exponential growth? And so the next method I want to talk to you about is quantum Monte Carlo. And I want to talk to you about one of the earliest quantum Monte Carlo methods, the determinantal quantum Monte Carlo method developed by Blankenbeckler, Sugar, and Scalapino about half a decade before high-TC. And the key application I'll show here is the two-dimensional Hubbard model. Okay, so this technique starts with the Hubbard-Strutanovich transformation. You have an interaction term that you want to get rid of, so you get rid of it by introducing an extra Ising variable that gets summed over, and you get a term here which is only a single particle term. Then you need to isolate this term in order to apply this, so you do a Suzuki-Trotter approximation to expand it into the product of two different terms, which is valid in the limit that this tau variable is small. And so you're left with this exponential of a single particle term with some sums pulled out. And so then you put it into a path integral. You get the partition function is the trace of e to the minus beta h. And you get a set of, you get an extra dimension to the problem, an extra time dimension that is all of these splitting of the system into different time slices from 0 to beta. And so you end up with something that you can think about doing a Monte Carlo with a sum over these Ising spin variables. Okay, so and the last step is you trace out the non-interacting fermions, and that gives you a pair of determinants. Okay, so the first question you'd like to ask is, well, if I'm going to try to think of this as a sum over probabilities, like Boltzmann weights. And so the first question is, why should a product of determinants be positive? Of course, a determinant is a large sum of terms with half positive and half negative. Why should you sum that up and get something that is positive? And it turns out, well, it's not necessarily positive, although at small beta or high temperature, it is rigorously positive. But more generically, you can keep track of the average sign of this probability, and you find that it falls off exponentially, an exponential with the inverse temperature and the volume of the system. And so that's the essence of the sign problem. It turns out that it's not so much that there is any negative signs, it's that the sign falls exponentially. You can deal with a finite average sign. It turns out that the statistical errors just get blown up by a factor of 1 over the average sign. Okay, so if it falls exponentially, then you're dead, but if it has some floor, then you'd be okay. Okay, now here's some results back from 1990 on the behavior of the average sign in a Hubbard model, a small 4x4 system. It's for two different dopings at u equals 4. And you see two very different behaviors. At the very highly doped case up here, that's a doping of a filling of 0.625. And the sign problem is not behaving very badly, and you can calculate things very well. But this is the uninteresting, in terms of the physics of this system, turns out to be particularly uninteresting, especially on this small cluster. The interesting regime with a doping of around 1/8 has a sign that falls off dramatically, and so you're very limited in what you can do for those systems. But you still, the scale here in beta goes to pretty high, and so you still have a region of relatively high temperature where you can answer some interesting questions. And so thus, Scalapino and his group back in the late 80s and early 90s were finding early signs of D-wave pairing back when it was more fashionable to think that it was S-wave. Okay, so generically we have this exponential growth in computation time for doped systems, but for half-filled systems, we have, if you have a system with a particle-hole symmetric model and it's half-filled, then it turns out that the determinant for the up spins is the same as the determinant of the down spins. And so you multiply them and you get a positive probability. And so here we've got my first example of something where we've carved out a set of problems where we beat the exponential and it's gone, and so we can solve the problem without the exponential. So if you think of this sign problem as this is a huge glacier, if you think of this sign problem as being this immense wall of ice, we've managed to break off a piece of it, these half-filled Hubbard models. Okay, so this application to the half-filled Hubbard model has been very useful over the years, to the early days of ITC. It's been very useful more recently in the case of the honeycomb system near a Mott transition. Let me mention before I go into these details that there are a number of other examples where you also have something that makes the sign always positive, so unfrustrated Heisenberg models. And then there's a lot of great work recently on models that have been engineered to have no minus sign. So you pick a model that has no minus sign, and then you try to find one that has the right physics. So here's this exciting work that led to a lot of work by many people, but this was the finding using this determinantal quantum Monte Carlo for the half-filled Hubbard model applied to the honeycomb lattice, think graphene, and the x-axis here is u over t. So for small u over t, we have a semi-metal phase. For very large u over t, we have an antiferromagnetic insulator. And near the Mott transition, there were results with this that found that there was a spin-liquid phase. And you can see the error bars are pretty big, and so it wasn't completely clear-cut. You see some gaps here, spin gap, but it looked like there was a spin-liquid phase. And so lots of people worked on related problems. No one else besides, no other methods besides this determinantal quantum Monte Carlo could really touch this problem. Now, is this really a spin-liquid? Well, this answer was yes, but then 2 years later, an even bigger calculation using the same methods by Sorella et al. Found that this, with bigger sizes, and these are really quite large sizes, 2,600 sites here, it appears to go away. And so it looks like the answer is that this phase doesn't exist. But from the computational point of view, these techniques were the same techniques, and and I think the lesson to take from this is that many of the problems that we're working on are really very hard. And so you really have to have large sizes to resolve some of these questions, and that we can't get around that the problems themselves are hard. Okay, so is there a general solution to the minus sign problem? And we just haven't found it. And so we can look at the computer science classification schemes. There's this classification NP for non-polynomial, which means that this is essentially an exponentially hard problem. And this classification scheme that most people have heard of is all based on the worst case scenario. So you look for the worst type of problem in that class and say, how hard is it to solve that? Okay, so this was applied to the sign problem by Troyer and Weiss. The conclusion is that if there were a general quantum Monte Carlo solver that beat the sign problem and could solve any sort of problem like this, such that it could find the energy as a function of the size of the system and the inverse temperature to an error epsilon in a time that only grew in this polynomial fashion, then we would have a solver that could be applied to things like spin glasses, which are very hard to solve and are known to be in this class NP, and there are mappings from those to many other problems, and so we would completely wipe out the NP class. And so this is almost certainly impossible, although it's not mathematically proved. But these are worst case scenarios, so this implies nothing about specific classes of systems that we can find a very good answer to. And this argument also applies not just to the sign problem itself, which is a feature of quantum Monte Carlo, but it applies to any other quantum simulation technique. So DMRG, PEPS that I'll talk about later, density functional theory, there is no general technique that solves all of those problems to an arbitrary accuracy in a polynomial time. Okay, but if we think about these hard problems, like the spin glasses, Mother Nature isn't very good at finding the exact lowest energy state in a spin glass either. So we might say, well, maybe we'll be able to find algorithms that can solve systems that at least Mother Nature is good at. And so if we think, for example, at optimally doped YBCO, it always becomes superconducting below TC. That's a problem that Mother Nature has no problem with. So we can hope that we could solve that sort of problem. Okay, so what distinguishes physical problems that nature solves easily, and can we devise algorithms that solve these problems? And a new answer to this, at least a partial answer, is that one of the features that physical systems have is low entanglement, at least in ground states. Okay, so here is an example system, a simple Heisenberg spin chain. The Heisenberg spin chain is considered strongly correlated. This is an exact diagonalization with 8 spins and 12 spins. Here are the energy levels of the system. You know, they grow, the number of them grows exponentially, so they get very dense. And then on the right, I show the entanglement entropy for every one of these energy levels. Here it is as a function of energy. And so the ground state is the lowest energy state, and we see here's the ground state, and its entanglement is quite low. And I'll tell you a little bit more about what the entanglement is in a minute. Notice that the excited states don't have this property. So if you go into the bulk in the middle of the black region here, you have almost the maximum possible entanglement. Okay, so it's a general rule that ground states have low entanglement. And in fact, these bulk eigenstates, which I would call super entangled, I would say these are unphysical states, because if you look at a state up here and you think of the energy time uncertainty principle, the spacing between those states is exponentially small. And so it would take exponentially long to actually prepare such a state or to measure such a state. So these we think of as unphysical, large entanglement. And so this sort of looks like it's making sense that we should look at low entanglement for physical states. So what is entanglement entropy? Well, the ordinary entropy, what we tell our undergraduates first, is that the entropy is minus kb times the log of the number of accessible microstates. I guess there's no minus sign. So it basically counts the number of states that the system might be in. Okay, what is entanglement entropy? Well, entanglement entropy depends on a cut dividing the system into two different pieces, and the entanglement entropy essentially adds up the log of the number of quantum fluctuations between the two sides of the system. Now, it turns out that counting up quantum fluctuations depends on what your axes are, what your basis is. So the rule is that you have to choose the axes or the basis that makes this the smallest number. And there's a specific technique called the Schmidt decomposition that puts the wave function into a diagonal form, and then it gives these wave function coefficients here. You square them and they look like probabilities, and then you can stick them into the standard entropy information formula and get the von Neumann entropy. So the key is that the entanglement entropy is counting the number of fluctuations between two parts of the system. So why should that be small? Well, that's a sort of a deep question, but one sort of answer is that high entanglement doesn't help the system get a low energy. And why is that? Well, it turns out that there's a property of entanglement called monogamy of entanglement. It's just like the word sounds. You can't be that close with many other people. You can't be in a strong singlet with more than one other spin if you're talking about spin 1/2. So if you waste a lot of entanglement with complicated many-particle entanglement over long distances, you won't be able to minimize the energy, which depends on short-range entanglement. Okay, this sort of idea is summarized in the area law, which says that the entanglement entropy is proportional to the area of the cut separating the two subsystems instead of the volume of one of the subsystems. And this area law is not something that's proven. It's sort of a general expectation which seems to capture the leading behavior. In fact, for Fermi liquids, there's a log correction. But there's a simple argument that if we think about a valence bond or an RVB state divided into two systems, the entanglement is not going to come from these states that are entirely within one side of the system. It comes entirely from the boundary, the states that you cut. So how do we make use of that to find a method that we can use to calculate properties? Okay, so the basic idea is that low entanglement means few quantum fluctuations across a cut. So if we cut the system, we can re-expand this system in terms of a small number of states representing those quantum fluctuations. And this sort of compresses the state. And then we repeat this compression on every link in the system, and we've compressed it in every possible place, and we've beaten the exponential. And so this is the matrix product state representation of the ground state, which probably almost all of you have heard about. So matrix product states is the wave function used by DMRG. DMRG is that plus the iterative algorithm to find the ground state, find the energy. So here's a matrix product state written as a product of matrices. So each of these matrices, it looks like a matrix, but it's got an extra degree of freedom, the physical, say, spin of the system. And so on every spin, you actually put two matrices, one for the up and one for the down. And then if you want to find out what the value of this wave function is, you just pick which matrices that are listed here and multiply that up, and you get a number. And it's a dramatic compression of a wave function. So on the left-hand side, we would have 2 to the n possible states. The matrix product state, if the matrices are m by m, we have n of them, then we have nm squared variables to store. And you can never, once you're working with these, you can never totally uncompress it because it would be exponentially large, but you can do quite well by sweeping back and forth. Okay, so let me now jump ahead to 2D systems and talk about, time's going fast, talk about some of the results for two-dimensional systems, both from DMRG and from one of these new methods, PEPs. Okay, so when you want to do a traditional DMRG method for 2 dimensions, you have to do this sort of unnatural thing of following a path. And the calculation time for doing this turns out to be an efficient calculation, but it's not a very efficient representation of the wave function. And so you tend to have large matrices when you do this for a 2-dimensional system. The new guy in town is this PEPs method. And the PEPs method, at every site, it gives you a tensor, and the tensor gives you direct connections to the neighboring sites, and through those connections, entanglement can flow back and forth, and without going through a roundabout path. So with these, you get a much more compressed representation, but they're also much harder to work with. So practical calculations here are limited to about a dimension of 15, but that turns out to be comparable to these results here for much larger matrices. Now, the calculation time for this grows much more rapidly. Okay, so let me show a few movies. Okay, so here's a result for the Kagame system treated with DMRG. And this is an example where the green dot is actually showing those 2 sites in the center going back and forth. And if you watch it closely, you'll see that it's actually following a funny path. What this is a purposefully biased calculation to try to show that this valence bond state, which was thought to be at one point the ground state of this system, it follows the dimers in the valence bond state. And because it follows the dimers in the valence bond state, it highly favors that state. And so this was a calculation to show that even though we highly bias it away from the spin liquid, it finds the spin liquid. And so why is it disappearing? Well, the red bonds are regions where the value of S dot S is above average. The blue ones were below average. And so when it disappears, everything is the same and it becomes a liquid. Okay. Let me just briefly show this. Let me skip this. Our chairman is standing there. This is a fun Stripe movie. But okay, let me say a little bit about this interesting work that Steve mentioned earlier that uses this PEPs method. Okay, so here are results for the TJ model, and it uses this natural wave function, this PEPs, and the finite size effects are actually none, because this one of the things you can do with this type of wave function is repeat the tensor out to infinity. And so the I in PEPs means that it goes out to infinity, and so there's no finite size errors. There's only an error associated with the dimension of the index on a tensor. So what you see here are the main IPEPs results dropping down as a function of 1 over this bond dimension, and we get some, I think this is 14. Going below the best previous variational Monte Carlo results. And one of the key takeaways of this result is that we have two different states, and we're seeing the very close competition that Steve mentioned in his talk. So the upper state is a uniform D-wave state, and the bottom state is a stripe state. And the stripe state is lower, but they're coming closer. And so it becomes very hard to tell the difference between these. And where would ordinary DMRG fit here? Well, it would depend entirely on the width of the cylinder. So if we were doing a width 8 cylinder, it would be a little bit better than these, and if it was a width 10 cylinder, it would be worse, and then beyond that, it would be much worse. Okay. Okay. Let me switch to where do we stand with this? Okay, so what can we do with these methods, particularly these tensor network methods? For many spin 1/2 2D frustrated spin systems, we can now determine the ground state phase diagram pretty well. So for instance, the Kagame system, honeycomb systems, frustrated square lattices. Other aspects of the problem can make things much harder. So if you go to higher spin or Hubbard models, say more states per site, that makes it much harder. Close competition between phases makes things harder. Log corrections to the area law, like for fermions, make it harder. So the Hubbard and TJ models have all of these complications. Nevertheless, we're now seeing the same competing phases in the simulations as in the COOP rates, as Steve emphasized. And then this PEPS method is sort of putting all of these phases on a very natural footing where you can see each type of phase. And so it's giving a very balanced view of this competition. And the last point I want to make is that these solutions that we're now getting for these models, I think, are about as good as the models themselves, or maybe better. The models that the Hubbard model, the TJ model, is a very oversimplified model. And it's amazing how well things like this work for many problems like the COOP rates. But to make further progress, it's not so much a matter of trying to solve this very approximate model better, but we need to get a better handle on the models themselves and then move them both forward, the models and the solutions. Okay, so to summarize, the numerical methods have made a lot of progress by finding classes of problems where the right algorithm can beat the exponential. And quantum Monte Carlo can now solve very difficult systems when there's not a minus sign problem. Tensor networks, which exploit low entanglement, can do very well in 1D and many 2D systems, even if there's a sign problem. And as I said, we still have to worry about this model problem. Thanks.
All right. Thanks, Steve. All right, so we have time for a few questions. If you have questions, please go to the microphone. I'd like to ask a question myself.
Yeah.
You were mentioning these variational results from, I guess, IPEPs on the Hubbard model with two states with very different symmetries with rather close energies. I mean, is it known, I guess in the same approach, you could probably also calculate overlaps in finite regions? I mean, presumably can one ask whether the states themselves are somehow close, or are they extremely different?
Yeah, I think you can ask that question, and I don't think that it has been addressed very much lately, but I think that's something that one could address, and I think we should address it.
All right, so please.
Yeah. Yeah, I have a question regarding what can you do with these methods. You are talking about finding the ground state, and one of the big issues that we have in condensed matter is finding dynamical properties. Is there any progress in that area?
Yeah, that's a good question, and that's another one of the areas that I had to leave out. The issue of dynamical properties is something that we can solve for the dynamics of one-dimensional systems now rather well with DMRG. It doesn't have difficulty working with So, for instance, you can time evolve and solve the time-dependent Schrodinger equation for a state as long as the entanglement of that state doesn't grow. The problem is that when you do solve the time-dependent Schrodinger equation, even if you start with a low entangled state, its entanglement may grow greatly. And so we're limited by entanglement growth. If the entanglement growth is not too big, then we can deal with the system. So as a practical matter for spectral functions, the entanglement doesn't grow very fast, and we can often do quite nicely for that. And so that work has mostly been focused on one dimension so far, but we are currently working on things like the Kagame lattice, working on extracting dynamics for it, for things like spectral functions.
Yep, okay, there's another question.
I know that DMRG nowadays is used also for theoretical chemistry calculation. Can you comment on that?
For theoretical calculations. Yeah, it's a very important development. It allows things like classifying spin liquids, classifying different types of long-range entanglement. You can set up a tensor network and that captures the say a topological order, and then work to renormalize down the tensor network to the minimal possible size, and that gives a characterization for that. But there's a whole variety of different types of applications. Some of them very far afield, and some of them I know very little about. So one of them that I know very little about is the Mira network is now thought to be relevant to holography in anti-de Sitter space, things like that. So lots of different applications. It's gotten so broad I can't keep track anymore. Certainly fascinating developments.
I might have misheard the question, but I thought the question was applications to quantum chemistry.
I'm sorry, I missed the question. Okay. So quantum chemistry is another application where I know something more about, in quantum chemistry, DMRG has found a niche. DMRG is now part of one of the big quantum chemistry codes, MolPro, and so it's used for particular types of molecules. It can do very large molecules that are sort of one-dimensional. It can do medium-sized molecules with often better accuracy than anything else that's available. So it has a very niche, and it's still developing in that area.
I think maybe one more question.
I have a more philosophical question maybe, because if you take, for example, the Hubbard model, the places where you expect to find fancy physics like strange matter or pseudo-gap behavior always turns out to be the places where the sign problem is the worst. So can you tell me, might there be a reason for that all the interesting physics always happens where there's a big sign problem?
We often had that same question back when we were just doing quantum Monte Carlo, and we wanted an answer for a doping of 0.15, and that was the place that the sign problem killed us. And I think that the answer to that never really went too much beyond philosophy. Mother Nature is out to get us, but I don't think we made too much more progress than that.
All right. On that note, I think I'd like to close the symposium. Let's thank Steve and all the speakers again, and the Kavli Foundation for putting this great event together.